Hi all, I'm going to go through the Bohr model extended. Some actually really good questions, really challenge your understanding of these IB problems. All right, so the first one, the answer is going to be A. Okay, so why did those energy level diagrams relate to this emission spectrum? Basically, if I look at the three possible transitions here, I've got two large energy ones, as designated by those large arrows. My alignment got a little bit off. Okay, that's a little bit better. And so large energies correspond to short wavelengths because E is proportional to 1 over lambda. So I should expect two short wavelengths next to each other because these two gaps are very similar, and then one particularly long wavelength that corresponds to a small energy. That's why this one is, why it's A, because the wavelength is increasing in this one. So I like that problem a lot. It's subtle but elegant. Okay, next one is this whole 1 over lambda that we did the derivation on. So good news is you don't have to do the derivation or even know all that, but we want to understand the significance of it, of what the N and M are. So first statement you should make, or one of the statements you make, is N and M are integers, first of all. Okay? And what do those integers refer to? Specific energy levels. So you got to make a statement like that or something to that effect. And then there's a minus sign in there, right? So what is the minus sign? And they're talking about, it's when electrons, that's what I do, well, I should say E's. When an electron transitions from M to N, a specific wavelength photon is emitted. In other words, I'm being very careful to refer back to why I'm referring to wavelength rather than, let's say, energy, because the equation has the lambda in it. Okay? And I want to talk about emission. So there's a lot of little things there. That would probably be a 3-point problem on an IB test where you got to have all those little details there. Okay, part B. Calculate the wavelength with the lowest value of wavelength, So the lowest wavelength corresponds to the largest possible energy. Again, that's the inverse relationship between energy and wavelength. And so the largest possible energy is when we go from 1 to infinity. Okay, infinity means you're escaping the atom altogether. So it's not 1 to 3, it's 1 to going away at infinity there. Anyway, so what we would do is say the energy of the photon is hc over lambda. That's going to be the difference between the energy levels. So I use the 2.28 times 10 to the negative 18th in the formula that they gave at the beginning. Sorry, I keep going back and forth here, right? So we're using this equation right there. So there's where the 2 point, and I'm putting in 1 for my first energy level, and then I'm going to put in infinity for my other energy level, and hopefully understand that anything over infinity is going to be 0. So it's really just the energy of that first level. And if you work out the numbers, looks like I did not put an answer there, we should get lambda is about 90 nanometers. Okay, so that would be 90 times 10 to the negative 9th. You probably have 9 times 10 to the negative 10th. That would be the correct answer in terms of meters, 9 times 10 to the negative 10th. So then determine the value of the Rydberg constant. So again, I'm going back to this equation which is given on the front. I'm plugging in 1 for n, and I'm putting in 0, I'm not plugging in 1 for n, but 1 over 1 squared is 1, 1 over infinity squared is 0, so this whole term is 1. So if I do the algebra, I can see that the constant is 1 over the wavelength. Whoops, I wrote that down wrong. No, that's right. I guess I don't know what I was doing there. And so if I do 1 over the wavelength that we found right here, we get 1.1 times 10 to the 7th per meter. So it's a large number. I'm tempted to say negative 7, but it's not a wavelength. Okay, so the last question in this, or this is a new question, what are the fundamental postulates that gave rise to the Bohr model? Okay, so the first one is that it's a stable circular orbit. That's what's given. All right, so what are the other ones? Key, probably the most important, actually two very important. Angular momentum is conserved, or I shouldn't say conserved, is quantized. Okay, so quantized in the equation is L is NH over 2 pi. And then And the part we've really been focusing on the most with the spectral lines is energy is emitted or absorbed, depending which way it goes, when you transition or when an electron transitions from one level to another. So you want to be pretty specific about that. 3 continued. This looks like a pain in the butt problem, but it turns out to be pretty easy. So we've got ways of expressing energy, radius, and velocity in terms of the energy level. So you see n is in each problem. You don't have to derive that. So they want you to apply it in the ground state. In the ground state, you got to recognize n is simply equal to 1. So if I put in 1 for all these, I get essentially the same numbers as the ones there. So those are the answers. Now, and I really like C, we can apply Heisenberg uncertainty principle to an electron in orbit, where they're telling us, and I hope this kind of makes sense, okay, that the uncertainty in the speed of the electron is approximately equal to the electron speed, right? Where the uncertainty in the position is essentially equal to the radius of the electron. Okay, so what we're basically saying is if you're not looking at the electron, you don't really know where it is. If you want to pinpoint where it is, in other words, at its radius, you're going to lose information about where it's going or where it's going to be any time later. So that gives an inherent fuzziness as to where the electrons are at any time. So that's a Heisenberg uncertainty. So we use our Heisenberg uncertainty principle for position and momentum. We solve for the uncertainty in the momentum where delta x is that radius. And notice our radius in the part above was 0.0529 nanometers. So I have to convert that to meters. That's where the 10⁻⁹ comes from. And so I get a very small uncertainty in momentum, and then I use the velocity and momentum relationship to get that velocity. And note that it's 10⁶ meters per second, which is very similar to what we see up here. It doesn't have to be the exact amount, but we see it's on the same order of magnitude. And then lastly, Bohr suggested that they're well-defined orbits. Well, Heisenberg came a decade, his idea came almost 2 decades later. So why is it a poor one? So what you got to make clear is that, I already said it, one assumption is it's well-defined. Okay? So what does that mean? That means delta x is very small. Or if, so well-defined means x is very small, then by Heisenberg's principle, then momentum, or the uncertainty in momentum is very large, or uncertainty in velocity. And you should reference Heisenberg uncertainty principle. Therefore, if our uncertainty in momentum, that makes the orbit much less defined. It's much fuzzier where the electron is going to go if I pinpointed where it is at one instant. So that's where that whole electron cloud idea comes from. So it's a nice subtle application of the uncertainty principle where we can kind of put numbers with that.